Welcome to Spring LIB.
For this problem, on the topic of electromagnetic induction, we are given the area as well as the separation of the parallel plates in a capacitor. We are also given the dielectric constant, the potential difference between the plates, the conduction current as well. And we are asked to calculate the charge on each plate, the rate of change of the charge on the plates, as well as the displacement current in the dielectric. Now, we know for a parallel plate capacitor, the charge on the plates of the capacitor, Q, is equal to C times V, where C is the capacitance and V is the potential difference between the plates. And we can write this as, by replacing C as epsilon times A over D, where epsilon is the dielectric constant, A is the area, and D is the separation of the plates. And that's multiplied by the potential difference V. Now, since we know these values, we can substitute them in, and we can hence calculate the charge on the plates. So this is the dielectric constant of 4.7 times the permittivity of free space epsilon naught, which is a constant, times the area of 3 times 10 to the minus 4, and that's square meters, times the potential difference between the plates of 120 volts, all divided by the separation between the plates, which is 2.5 times 10 to the minus 3 meters. So calculating, we get the charge held on each plate to be 5.99 times 10 to the minus 10 coulombs. And that's our first solution. For part B, we want to calculate the rate of change of the charge on the plates. So the rate of change of charge is dq dt, but we know dq dt is actually the conduction current IC. And so dq dt, which is the rate at which the charge is changing, is 6 times 10 to the minus 3 amperes. And so this value is given, the conduction current is simply 6 milliamperes. Now, lastly, we want to calculate the displacement current in the dielectric. The displacement current is JD, and JD we know is the dielectric constant epsilon times the rate at which the electric field strength is changing, dE dt. So we can write this as K times epsilon naught times the conduction current IC divided by K times epsilon naught times the area A. So this is in fact the conduction current IC divided by the area A. And so this is simply JC. So that's the current density, the conduction current density JC. So this means that since the displacement current density and the conduction current density are the same, we have that the displacement current is equal to the conduction current, and this is 6 times 10 to the minus 3 amperes.